very happy to be here, and I'm going to tell you about using deep generative models to simulate molecules. And I'm going to start with a brief description of what we want to do. We're interested in sampling from the probability of 3D atomic configurations of molecules. Molecules are made by atoms. Atoms can be in different coordinates in space, and typically they are going to occupy different configurations according to this Boltzmann distribution that we have here. Let me see if this works. Yeah. It's going to be exponential of minus some energy times some constants. And this is useful because if we can simulate molecules and we can know the 3D atomic configurations of molecules, we can know what's going to happen in the real world. And this is very important, for example, in drug design. If you want to design a new drug that is going to bind to a target, maybe you want to simulate things and know if your drug binds to the target. This is an example of a website from a company that does simulations of molecules. And what we have here on the right is a big molecule, a protein, and a small drug-like molecule that is around it. And we see that at some point it binds to some location. And the atoms, obviously, they are not fixed, they are not rigid, they are vibrating. They are vibrating because they are in vacuum and there is nothing stopping them from moving, okay? So we're interested in doing this type of simulations, okay? And the typical approach to do this type of simulations is to use Markov chain Monte Carlo techniques. These techniques will allow us to draw samples from a particular probability distribution. So we have, as what we saw before, we have access to this energy. This is going to be given by a model, a physics-based model to us, and we are kind of ignore where this comes from, but we are seeing that we have access to these energies. Given these energies, you can then use Markov chain Monte Carlo to draw approximate samples from this probability distribution, okay? And Markov chain Monte Carlo is going to generate a Markov chain whose stationary distribution is going to be the target. Here we see samples from the Markov chain in green, and the target is this Gaussian, and the marginal distribution of the samples of the chain agrees with the target, okay? Who has seen Markov chain Monte Carlo before? Who is familiar with these methods? Okay, almost everyone is familiar, so I'm going to move a bit fast on this. So yeah, there are different ways to implement Markov chain Monte Carlo methods. Typically, you want methods that satisfy detailed balance. If you sample from the target and you apply your transition operator from your Markov chain Monte Carlo method, that probability has to be the same as, you start at x, sample from the target, you apply the transition operator and move to x prime. That should be the same as sampling x prime from the target and applying the transition operator to go from x prime to x. If you have an operator that satisfies this condition, you can show that it's sampled from the target distribution, and Metropolis Hastings is probably the most widely used method to do this. You have seen Metropolis Hastings? Who has seen Metropolis Hastings here? Many people. Okay, good. So it's a very easy way to implement Markov chain Monte Carlo methods. And typically, you start by having a proposal from something simple like a Gaussian. You change your state a little bit. From x, you go to x prime. And then this is your proposal, and you do this, you calculate this acceptance probability as the minimum of 1, and this ratio between being at x and transitioning to x prime, and being at x prime and then transitioning at x. And then you will accept x prime, the new proposal, sample from this Gaussian, with this probability. And if you accept, that's the new state in your chain. And if you reject, you just stay at the previous state. So the state is duplicated, okay? This is a very important thing, and it's probably the most widely done back implementing Metropolis Hastings. You need to duplicate the state if you reject, okay? If you just don't do anything, you won't sample from the right distribution, okay? Good, so this is great, but Metropolis Hastings is slow, especially if your target is correlated like this, because sampling from a Gaussian, you do small changes to your state, and you have to accept, reject, and the time it takes for you to move along this correlated Gaussian is going to take very long. There is a solution to this, and there is a better method, which is called the Hamiltonian Monte Carlo. Who has seen Hamiltonian Monte Carlo before? Many people as well. So Hamiltonian Monte Carlo improves over Metropolis Hastings by replacing this Gaussian proposal with just a simulation of Hamiltonian dynamics. Okay? The idea is that you have your target. We saw that the target is exponential of minus this energy. That's going to be some potential energy, and you're going to add some kinetic energy, which is going to be some quadratic function of auxiliary variables, V. And you're going to be now drawing samples from the potential, from these velocity variables and from the position coordinates, and just simulating Hamiltonian dynamics. I'm going to go a bit fast on this because it's not so important for what I'm going to focus, and it's just a bit of background. But the idea is that instead of proposing from a random walk Gaussian, which is what Metropolis Hastings with Gaussian random walk is doing, we're going to simulate Hamiltonian dynamics using as potential energy the target distribution, okay? And you can just implement Metropolis Hastings with these Hamiltonian dynamics transitions, and this is probably the state-of-the-art method for Markov chain Monte Carlo, okay? It's going to reduce a lot the rejections. You can simulate the dynamics using Leapfrog, and the key thing is that it's going to do, Hamiltonian Monte Carlo is going to do very fast transitions. So here, for example, instead of having to do this random walk, we're going to be moving in an expanded space following Hamiltonian dynamics. And Hamiltonian dynamics, they preserve the total energy, and that's going to make the acceptance probability Metropolis Hastings very high, okay? I had a small video demo just to see the difference between Hamiltonian dynamics and Markov chain Monte Carlo. And this is a video that was done by some PhD students from the Cambridge group quite some time ago. In particular, David Dueno. He's now a professor at Toronto. He's actually one of the guys that came up with some of the methods that I'm going to describe tomorrow. And we're going to see now this demo. It's just it's based on this Harlem Shake meme video. I don't know, do you remember the Harlem Shake? Who remembers this Harlem Shake? So these were some videos that became very popular on the internet, and the idea is that you had this song, and at the beginning there is like some small rhythm in the song, and you have some people in the video doing something, and then the music changes, and then you were supposed to see many people doing crazy things when the music changes, okay? So this is kind of the same thing. So in the first part of the video, when you have the first type of music, you see Metropolis Hastings with Gaussian random walk proposals, and you will see that your samples are not going to, your Markov chain is not going to move that much, okay? The idea is to sample from these probability distributions that kind of are the letters of Harlem Shake. They're kind of Gaussians that form these letters. And with the random walk Gaussian proposal, we are not going to move much. Because if you want to make large steps, you will move into regions of low probability and you will be rejecting. And with the Hamiltonian dynamics, you can move much faster, okay? And we're going to see that when the music changes, you'll see the Hamiltonian dynamics and the samples are moving quite a lot. So let's have a look at the video. I think the sound should work, so let's see this. Is this working?
Con los terroristas.
So this is Metropolis Hastings with Gaussian corrector. And the particles don't move much. And as the music changes, and this is Hamiltonian Monte Carlo, and you see that the transitions are way longer in terms of the distance that the particles. Okay. So that's it. It's a cool video just to see the difference between these two methods. So Hamiltonian Monte Carlo is the state-of-the-art technique to do samples, to obtain samples. And actually the simulation that we have seen at the beginning has been done using this type of method. And it's what is used in practice at the moment, okay? But Hamiltonian Monte Carlo and Markov-chain Monte Carlo methods has limitations. And one of the problems is that it can get stuck into local modes. Even though these Hamiltonian dynamics help you make larger transitions as you run your Markov chain, if you have two modes that are far away one from the other, then it's very hard that you will move from one to the other. You could have a distribution that is like this, and then here there is another mode. And even if you run Hamiltonian Monte Carlo, you will be drawing samples here, and the probability that you move and start generating samples from the other mode is pretty low, okay? The samples that you generate are still correlated, okay? With Hamiltonian Monte Carlo, you reduce these correlations, but you will still have correlations between the samples, meaning that to generate independent samples, you need to run a very long chain, okay? The other thing is that Markov chain Monte Carlo, whenever it needs to generate a new sample in the chain, a new step, it forgets about everything you did in the past. Even if you spend tons of compute generating thousands of samples in the past, the next sample is using only the previous one, okay? And that seems to be wasteful. The other thing is that to guarantee acceptance, typically you need step sizes, smaller step sizes. This happens with the simulation of molecules. The step size in your Hamiltonian, in your simulator of the Hamiltonian dynamics has to be small. Otherwise, very often you end up into unphysical states. Your simulation diverges, and you will be rejecting all the time. So the way people run simulations of molecules in practice is by doing this Hamiltonian dynamics, but with super tiny step sizes to avoid divergence. And this means that sampling molecular events that take long amounts of long times, then you need a lot of compute, and you need to run very long simulations. So the alternative to this is to look into deep generative models, okay? Deep generative models, the idea is that we have here our target distribution. This is where we want to sample from. It's very hard, but what we can do is to have a model that receives here tractable noise. This could be Gaussian noise, for example. We're going to throw that into a big neural network like this one, and we're going to get some approximate samples that are going to look like exact samples from the target, okay? That's kind of something that you could think of doing. And the advantage is that the samples generated by the model are independent, and you do it in one shot, okay? You have tractable noise at the input, you get sample at the output, and that's it. And in principle, you wouldn't have to generate this long simulation that Markov chain Monte Carlo has to do. That sounds great. We have seen a lot of advances in deep generative models and in generative AI recently, and there is a lot of promise of using these techniques to simulate molecules. You could imagine that in the future, molecular simulations couldn't be, maybe they are not run the same way as they are done at the moment, in the same way that you have this generative AI that will receive maybe a prompt, and it's going to generate an image of a dog, or whatever that we write in the prompt. You could have a prompt specifying the conditions of your simulation, like what you have here. Maybe you want to simulate a protein with this sequence, and a drug-like molecule with this particular structure in water at some particular temperature, some pressure, and other conditions. And then your generative AI method is going to generate the simulation for you, and this could be ideally faster than running the Markov chain Monte Carlo techniques. This sounds great, but there are many challenges to achieve something like this, okay? First, deep generative models, the ones you have seen probably on the internet, these, I don't know, all these fancy images generated by AI, they have been generated by models that were trained from data. You have data with millions of images, data with, I don't know, tons of seconds of video, And the models are trained on that data, and they can generate new data that is similar to what they saw at training time. In this case of simulating molecules, you don't have access to data. What you have access is to these energy functions of the 3D configuration of atoms in space. Okay, so you need to train the models now from energy and not from data. How to do that? There are plenty of research opportunities there. You need to encode also imbalances in your models. Molecules are the same if you rotate them, if you translate them in space. You want your models to capture those imbalances. Your distributions can be multimodal. The molecules are not going to be doing just one thing at a particular time. They could be doing maybe something now and then later something slightly different. You're going to have multiple modes in your Boltzmann distribution. And you want to sample from these multiple modes that can be far away, and you want to do that efficiently. Your model makes mistakes also. The samples that it's going to generate are not going to be perfect. You may want to reduce the bias in those samples. How to do that? You want models that will generalize to that scale in high dimensions. If you simulate molecules with many atoms, the dimensions are 3D spatial coordinates for each atom in your molecules. The dimensionality can grow quite fast if you have bigger and bigger molecules. You want models that will be scalable and work well in higher dimensions. And you may want to train a model for a particular problem, but maybe you want your model to generalize to new settings of your problem. Imagine that you want to simulate this small drug-like molecule trying to bind to a protein. Maybe you change the drug-like molecule with a different one. Is your model going to generate still accurate samples? What happens if you change the protein? You want ideally models that generalize to new settings. All these are very important challenges and very difficult, but I think the field is improving, and we are seeing now methods that are getting better and better and solving more and more difficult problems, and eventually maybe all of these problems could be solved by these deep generative models. Today I'm going to tell you about some method that addresses some of these problems. It's not going to be scalable, it's going to work on a small molecules, but we'll see that many of these problems can actually be solved. I'm going to present this work done by some of my PhD students and postdocs and collaborators. It's a bit old, but it has some very nice introductions to the problem, and tomorrow we are going to see more advanced things that are newer as well. Good, so we want to use deep generative models to describe molecules. The first thing is what type of model we are going to use. There are tons of generative models. You may have heard about variation autoencoders, normalizing flows, diffusion models, flow matching, GANs, I don't know. There are many options. Here, I'm going to focus on normalizing flows for different reasons that are going to be useful in our setting. They will give us densities of the generated samples. You have a normalizing flow, and it will be able to give you the density of the samples that it generates, and that's going to be an advantage. We're going to see later on that these normalizing flows can be generalized to be very flexible, and some of the recent generative AI methods, they are based on this concept. You may have heard about flow matching. It's based on similar principles. So normalizing flows, they work as follows. We have a base distribution that is going to be easy to sample from. It's going to be this distribution here. It could be a Gaussian. And what we are going to do is to do nonlinear transformations of these of samples from this distribution in an invertible way. So we have a function f that transforms the sample x into a new variable y in a way that is invertible, and we are going to have access directly to the density of the new variable y through the formula for the change of variables. It's going to give us the density of a transformation of our variable. We're going to see later where this comes from. And typically this function f, because it has to be invertible, we will want to also reduce its flexibility so that computations are tractable. Okay, we'll have to, in this point, to calculate the change in density, we are going to need to do some calculations, and we want these functions to allow us to do those calculations fast. So we will have some form of simple transformations, but we are going to concatenate one after the other, in the way that after applying many of these transformations, each one with a simple function, at the end, we have a very complicated transformation. And it's going to map the tractable distribution P into something much more complicated, P of y, okay? Good. So let's see how this works in practice. In particular, how do you get the change in of variables formula? How many of you have seen this formula for changing variables with densities? Okay, many have. I'm going to describe this briefly just for intuition of where this comes from. So what happens is that your transformation is invertible, and obviously probability mass will be preserved. So if you have a particular interval here, if you have this interval, let's sorry. If you have this interval here, this is a unit interval in the X space, and then I apply my transformation F, and I'm going to a new space where the variable Y lives, and the interval is mapped now to this other one. Probability mass will be conserved. If this is P of X, this mass of this interval has to be the same. If this is P of Y, has to be the same as the mass, the probability mass for this other interval, okay? And this means that if I have a very small interval, d of x, times my Gaussian density, the probability mass of falling in this interval d of x is going to be the product of the density times the interval, and the same thing should be for y, okay? And you can just then divide the tiny intervals, and you will have that P of y is going to be the same as P of x, dx, dy, and this is the same as P of x, 1 over dy, dx, and this is the derivative of my transformation, okay? So that's where the intuition of where this change of variables formula comes from. You need to use the absolute value to be careful, because the derivative can be negative, and this is an example, no? So you have this interval, but then maybe x plus dx goes to y, and x goes to y plus dy. And then in this case, the derivative is negative, but the probability mass should be the same, and obviously you're not going to get negative probability mass, so you need to use the absolute value, okay? You can generalize this to multiple dimensions, and in this case, you're going to have not like a one-dimensional interval. Instead of a one-dimensional interval, you're going to have like a two-dimensional interval, like a square, like this, and it's going to be mapped to a parallelogram, and you will need to calculate the ratio between the areas of this probability of these spaces. You have like this could be here the x1, the x2, and it's going to be mapped through a linear transformation into this parallelogram, and the area of that parallelogram is going to be given by this determinant of the Jacobian. So in the end, the formula is going to be more or less the same as before, but instead of just the Jacobian of this derivative, you will have now, the absolute value of the derivative, you will have the determinant of the Jacobian. Okay, the Jacobian is just the derivative of the outputs of our function with respect to the inputs. The function now is multidimensional because we are working on multiple dimensions, and yeah, you will have how each of the dimensions in the output of the function f1 to fm changes as a function of the inputs x1 to xm. It should be the same dimensions in input and output. Good. Any questions so far on this? Everyone is happy?
One question?
Yes.
So you're thinking of each f as being like a little tilt towards that energy function?
Not really. So these f's probably, yeah. So what the functions are going to do is to try to drive the samples from the base distribution here, which is kind of Gaussian, into samples from the original. Okay, how this is done, it could be done in different ways. We don't really care a lot, but yeah, they're going to transform the samples in a nonlinear way. We're going to see more later on this and tomorrow on how to do this in practice. Good. So we do this, and now the question is, how do we get these transformations? What model you use in particular for the invertible transformations? What we're going to choose here is a very flexible transformation called neural spline flows, and it's based on the concept of a coupling layer. One of the important things in these normalizing flows is that you want to be able to calculate the change in density fast. And the change in density requires this determinant of the Jacobian. The Jacobian is going to be a matrix which is number of dimensions times number of dimensions in size. So the determinant, if you just do it for any function, then the cost of that is going to be cubic in the dimension. And that's bad. That's bad because cubic in the dimension is going to limit a lot the dimensions. You won't be able to work in high dimensions, basically. So you want to calculate this determinant fast, and the concept of coupling layer or coupling transformation allows us to do that. The idea is as follows. We're going to have here the input to the transformation, x, and what we're going to do is to split x in two parts. One part that contains about half of the dimensions, x left, and another part that contains about half of the other dimensions, x right, okay? And the transformation that we are going to do now is for x left is very simple. We do nothing. Sorry, for x right, we do nothing. Okay? X right is not changed by the transformation. Okay? And now x left, each of the entries in the left part of the vector x, we are going to transform them in a nonlinear way. In a way that they depend on the values of x right. Okay? And we are going to obtain a new vector, y, where the right part of y is the same as the right part of x, and the left part of y is the result of doing these nonlinear transformations dimension-wise as a function of the right part of x. Okay? Why do you do this? Why do you do this kind of fancy transformation? There is a very good reason. The reason is that the determinant of the Jacobian of this transformation can be calculated very fast. It can be calculated very fast because if you think about the Jacobian, you are going to have here x right. For example, let me see what was the. So we have f and then x. Okay, so this will be y right, and this is sorry. So let's assume that this is y left, y right, and then I have here x left, and then x right. Okay? And now, what is the derivative of y right with respect to x right is going to be the identity, okay? Because y right is the same as x right, and the derivative of the entries in y as a function of the entries in x is going to be 1. So here we are going to have just a diagonal entry. These are going to be all 1s, and then this is 0, okay? And now we can think about how y left changes as a function of the inputs, and y left is going to depend obviously on the corresponding entry in x left. So here we're going to have some non-zero entries, and then here I'm going to have zeros and zeros. And now each of these y left is going to depend also on the values of x right. Okay? So all these entries here in my matrix, here they are going to be non-zero as well, but all the other ones are 0. And this is now a triangular matrix. And the determinant of the triangular matrix is now the product of the elements in the diagonal. Okay? And that's going to be then very easy. That's going to make very easy to calculate the determinant. Okay? Is this clear with this coupling transform? Yes? Good. So now, how do you get these dimension-wise transformations? The idea is to use splines. You use a spline model like this. A spline is just a set of degree 3 polynomials, and they are specified by these nodes that appear here in black, and the slope at the nodes, at the nodes. Okay. You are going to get all these parameters, the locations of the nodes, the slopes of the nodes, as a function of the x-right positions using a neural network. So a neural network looks at x-right, and it tells you the nodes and the slopes, and you get this transformation so that I have here now one input like this is going to then be transformed to a new value like this one. Okay? And the good thing is that because these are polynomials, low-degree polynomials, inverting the function is very easy. And you can do it analytically right away. You get here the inverse right away. Which means that I have the inverse of my function, and that's going to be necessary to calculate the densities. To calculate the densities, I am given y, and then I need to use my formula here. I am given y, and then I need to get the corresponding x. I need to invert my transformation. Okay? And I will need the Jacobian of the transformation. I can do that very easily with this neural spline flow. I can also sample easily by just applying the transformation to samples from x. I sample from my base distribution, it could be Gaussian, and then I transform that to obtain y. Good. Any question so far? No? Good. How to encode invariances in the model? We can use internal coordinates. We said that molecules are invariant to rotations, translations. What we can do is start by placing one atom at the origin. Okay? So maybe this atom A is placed at the origin, and I'm going to say that the second atom, B, is going to be at distance from the first one. And the next atom, C, is going to be another distance, C, from B. And there is going to be an angle, I don't know, let's call this theta, for example. Okay, between this. And then I can add another atom, D, another distance from the previous one with another angle, and then I can have this dihedral angle between the planes A, BC, and BCD. Okay? If you use these internal coordinates in terms of distances and angles, you are fine. You are not really affected by changes in translations or locations. You just have one atom always at the origin, and then you place the other ones in reference to that one. Good. So you can use now these coordinates to represent molecules, and you are invariant. And the only thing is that you need to work with these normalizing flows on circular coordinates, in the sense that the angle, for example, the density in my model, the density for minus pi and pi has to be the same, and that's why this thing here is the same. Okay. You need to capture this, and the good news is that these neural spline flows can capture that, because in your transformation, if you have some uniform distribution, the derivative of this line in blue is going to determine the density after the transformation, and you just want the transformation at minus pi, for example, here, to be the same as the density at minus pi to be the same as at plus pi, you just need to say that the slope here at this node and the slope at this node have to be the same. You can do that very easily in the neural spline flows. Okay, so you can introduce these imbalances very easily into the model. Any question? Yes.
So over here, x and so you're vectorizing the x and the y, even if it's inherently in a higher dimension. Is that right? So aren't you losing the structure that may be there in the like higher dimensional thing?
Yeah, just to clarify, we don't change the dimension here. So x and y, they all have the same dimension. You always operate in the same number of dimensions.
So what does left and right mean? This one?
Yes. So it would be, imagine that you have a 100-dimensional vector. X left would be the first 50 entries in your vector. And then X right are the next 50 entries. So you just split, that's why the Jacobian had this particular structure. You just split the vector in these parts. Good. Any other question? Yes?
Is this rich enough? I mean,
Yeah, good question. It's very flexible, and I don't think there are results on the flexibility of these coupling flows. I think there are some flows that you can demonstrate that they are fully flexible. These ones, I think there are no theoretical results, but empirically they are very flexible and work better than others. So people use them. Yes.
so because you have just a pass on the text.
Yes, that's right. It's not fully clear. I think there is no theory telling you here how flexible this is, but they work amazingly well, and people just use them anyway. Good. So we have imbalances, and now another interesting thing is how to eliminate bias in your samples. It turns out you can eliminate bias using something called importance sampling. Have you heard about importance sampling before? Who has heard about this? Some people. The idea is very simple. So imagine that you want to estimate some particular expectation of a function with respect to your probability distribution P of x. That's the same as this integral. And now instead of sampling from x, from the true distribution, you are sampling from an approximate distribution from your model. Okay, so you sample from Q, and what you can do is correct the bias in your samples by including these weights. This is going to be the density ratio between the target P and your model Q. Okay, and if you draw a bunch of samples from Q and then reweight them with these important sampling weights, the average is guaranteed to be unbiased on expectation. The value of this average of weighted samples is the same as the true value that you want to estimate. Okay? So you have now here important sampling weights, and you can eliminate bias. This sounds great, but you need to be careful. You need to be careful with important sampling because you are reweighting your samples with these weights, and what can happen is that you can increase variance. Okay? Your bias is 0, but your variance can increase a lot. You could even have infinite variance in these estimators, which is not great. If you have infinite variance, it doesn't matter how many samples you have, you won't get the right solution. So you have to be careful with this, but the same way that you can get infinite variance, you can get 0 variance in an important sampling estimator. And you can get 0 variance if you look at what is the optimal importance sampling distribution. The optimal importance sampling distribution for this quantity is this. It's just a distribution that is proportional to whatever you want to integrate. Okay, here we want to integrate f times p. If we make our proposal f times p with some normalization constant, if you only have one sample from this optimal importance sampling distribution, you can calculate the value of the importance sampling estimator, and that's going to be the sample here that we have. This is the sample, f evaluated at the sample, and now here we have the density ratio, and you just have f times p divided by q optim, and q optim is f times p divided by the normalization constant, and the normalization constant is precisely what we want to integrate, which is what we get here, the normalization constant. So just with one sample, it doesn't matter the sample that we have, we get the right estimator. We have an estimator with 0 variance, only with 1 sample. Pretty amazing. But you need to get this optimal importance sampling distribution, which is not easy. Okay? So we're going to be using this in practice. Any questions so far on importance sampling? No? Good. So importance sampling is great, but when there is not a lot of overlap between your approximation Q and the target P, you can have high variance. You can reduce variance by using something called annealed importance sampling. And this is like a pretty amazing method. It's pretty amazing, this method. It was proposed by Radford Neal. Radford Neal, you could say that he's like a Monte Carlo genius. He was the one that proposed the Hamiltonian Monte Carlo in machine learning. He proposed this to use it in neural networks. And he proposed this way to reduce the variance of importance sampling. And this is kind of the thing that you see of geniuses, that they do this lateral thinking, that you don't really solve the problem right away, and they come up with something that actually solves the problem, but you don't see exactly how it is done. So this is kind of an example of that. Annealed importance sampling reduces the variance of importance sampling by a big amount. And it works as follows. Instead of generating samples from the target right away, what you are going to do is to create intermediate distributions here by doing a combination of the original distribution P and your proposal with some of these coefficients beta that go between 0 and 1. So the betas go from 0 to 1. So when the beta is 0, you have your proposal, and when the beta is 1, you have the target. Okay? And what you are going to do is to start sampling from your proposal and then do importance sampling not to the target right away. You are going to do importance sampling to the next intermediate distribution. Okay? And you are going to combine this with a Markov chain Monte Carlo. So the idea is as follows. You start by sampling from your proposal, pi 0. Pi 0 is the first intermediate distribution, is your proposal Q. You are going to target the next intermediate distribution, pi 1. And that's why you combine, you calculate this importance sampling weight, the ratio between the next intermediate distribution, pi 1, and your proposal, pi 0. This sample, x0, with this weight, is an unbiased sample from pi 1. And what I can do now is to do Markov chain Monte Carlo targeting pi 1, starting with this weighted sample. And Markov chain Monte Carlo leaves the target invariant, and it's going to give me another sample from pi 1. So as follows. I start with pi 0, I generate a sample, x0, I eliminate the bias in my sample by doing importance sampling with pi 1, and then I generate another sample from pi 1. It's an exact sample with a weight of x0, okay? And then I have my exact sample, x1, my exact sample from pi 1, and I do importance sampling with the next intermediate distribution, pi 2. And then I run Markov chain Monte Carlo targeting pi 2 to generate x2 and so on, okay? So it's like doing importance sampling, but not right away with the target. You do it step by step, and you put Markov chain Monte Carlo in the middle to change your sample a little bit. This is going to help a lot, because if you have, for example, imagine you have to, your proposal Q is like this, and the target P is like this. If you do importance sampling, you'll get garbage here, because all your samples here from Q will be in this case, and there is no overlap with P. So there is no way you can estimate something accurately, because your samples, they don't really cover P. But here in annealed importance sampling, you have MCMC methods driving your samples, and you will be able to move your samples to make them have more overlap with P. Okay? If you calculate the product of all these importance sampling weights, you get a final importance sampling weight for the final sample that you obtain. And you can show that the variance of these importance sampling weights will be smaller. I have a demo here of how this works in practice. Imagine that you have this target in blue. So the target here is this distribution in blue, and it's a mixture of two Gaussians. And your proposal is in green. Okay, so this is Q, this is Q, this is P, this is P as well in blue. Okay, there is not much overlap between Q and P. If you do importance sampling, most of your samples have 0 weight, and only a few ones here in the corners they have higher weight. This means that you will have very high variance in your estimators. And you can see here the importance weight value and the histogram, and you see that there is a lot of variability in the importance sampling weights. Some samples, most of the samples have very low weights, and only a very few of them have higher weights. If you do an yield importance sampling, what happens is that you start with these samples in green, but you move them slowly towards the target, doing importance sampling and MCMC with distributions that are closer to each other. You will end up with these samples now, here in blue, that have way more overlap with the target. And you can see the balance of the importance sampling weights, the distribution of importance sampling weights is now way more concentrated. Okay? You can reduce variance. You have still unbiased estimators, but you need to do a bit extra compute to run the MCMC methods. But it works in practice. Good. Any questions on a yield importance sampling? No? Yes?
Is this similar to sequential Monte Carlo? I'm very expert on these things.
Sorry?
So sequential Monte Carlo, is that related?
It's related. You could also see what an yield importance sampling is doing as a type of sequential Monte Carlo. In sequential Monte Carlo, you have some samples and you are updating them in an online manner. And you can think that an yield importance sampling is doing that as well.
And this is doing it on a single sample. Sequential, I guess you have a population you start with. Is that right? Individual is one trajectory.
Yes, that's right. So yeah, so you could even do. I mean, yeah, you could even improve over an yield importance sampling by having a batch of particles, and you do exactly the same thing as I mentioned before, where each particle is moved forward by doing this combination of MCMC and reweighting the sample, and then you could do resampling across particles, which is what you do in sequential Monte Carlo. Good. So now that's great. You can eliminate bias in this way, but how do you train your model if you have access only to energies? Yes, one question. Yes.
Why do we care about the variance of these weights?
Can you repeat why?
Why do we care about the variance of these weights?
Why do you care about the variance? Yes. The variance of the weights is going to be related to something called effective sample size. The effective, yeah, so effective sample size will be, you draw maybe 100 samples, but maybe only one of those samples has a very high weight, and all the others have very low weight. In that case, your effective sample size is 1. Even though you generate 100 samples, only one of them is representative, you will have very low effective sample size. And the balance of the importance sampling weights is directly proportional, is directly related to the effective sample size. Think about this. If all the weights are the same, 1 over the number of samples, you have 0 variance in your importance sampling weights, and the effective sample size is maximal. And you can show that the variance will be maximum when only one of the samples has the largest weight, and all the others very low weights. Good. So how do we train the models now if we don't have access to data, only to energies? There is something that you could do, and it's try to minimize the Kullback-Leibler divergence between your model, Q, and the target. I assume you have seen this because it's widely used. Who has seen this Kullback-Leibler divergence? Many people. No, it's very widely used. So the advantage of this is that the divergence can be written as an expectation with respect to samples from your model. And you can write away samples from your model. You can evaluate this objective, taking this log density ratio between Q and P over a few samples from Q. P, it could be, you don't need the normalized version of P. Up to a constant is fine. So you could try to minimize this objective. And the question is, why don't we use this? We don't use it because it doesn't work. It doesn't work for a very good reason. This divergence measures the error. The error is like this log density ratio. When the P and Q are the same, the ratio is 1 and the log of 1 is 0, so the error is 0, the average of 0 is 0, your divergence is 0, you have a perfect fit. When this is not 0, how much it matters depends on the value of Q. Because if Q gives you very low density in some regions, if your error is high there, you don't care. Because the whole thing is an integral where the error is weighted by Q. And this is what happens here. This is a target distribution with many modes. And we see that here, I am not generating any samples. My model is only sampling here in blue. These are samples from my model. It's covering some of the modes. In other modes of the target, I never sampled. The density of my model there is 0, but I don't care because the error is weighted by my density. So this thing can have a low Kullback library divergence in this way and still produce bad samples because you don't cover the missing modes. Okay? So we need something better to solve this problem. And in this work, what we propose is to use a different objective that will cover all the modes. In particular, we minimize something called the alpha divergence, and this is a divergence that is said to be mass covering. Okay, it will try to cover all the different modes, and this one here, the Kullback library divergence between Q and P, is going to be mode seeking. The alpha divergence actually for different values of this parameter alpha will produce results that are mode seeking, like this one where you fit with a single mode distribution, you try to fit a two mode distribution P, you cover only one of the modes. But if you increase the value of alpha, you move to mass covering solutions where you try to cover all the modes of your distribution. So what we are going to use is this alpha divergence with value alpha equal to 2, and that's more towards mass covering, and it's going to avoid the problem of missing modes. There is also a very big advantage of this alpha divergence. You can show that the alpha divergence with alpha equal to 2 is precisely related to the variance of my important sampling weights. Okay? It's the expected, is the second moment, but I mean, you don't care about the first one, so this is more related by the variance. The first moment of the important sampling weights will always be the difference in normalization constants between the distributions. So you don't care about that. And then this expected square of the important sampling weights, if you minimize that, you will come up with a model Q that has minimum variance when you do important sampling, and that's great. Yes. So we want to minimize variance when doing important sampling, and minimizing this objective will cover all the modes and will result in a model where you have minimum variance as well when you do important sampling. Any questions on this? No? Good. So the other thing that is a bit tricky is how to optimize this alpha divergence. And it's complicated because the gradients have high variance as well. Okay? But we can do something interesting. We can try to generate samples from the optimal important sampling distribution. So the divergence is like this. And obviously, you cannot solve this integral exactly. You can approximate it by drawing samples from a distribution and doing important sampling to estimate the integral. Okay? What you can do is use the optimal important sampling distribution, and we said that the optimal important sampling distribution is proportional to whatever you want to integrate. You want to integrate p squared over q. Your optimal importance sampling distribution will be p squared over q. And we'll try to draw samples from this to do importance sampling to evaluate the gradient. The key thing is that you cannot really sample from this directly, but you can run an yield importance sampling targeting this distribution. And this is kind of the key contribution of this work. You want to estimate the alpha divergence with low variance, and you can do it using a yield importance sampling targeting the optimal importance sampling distribution for this divergence. So we target p squared over q when we draw samples with an yield importance sampling. So we sample from our model, we create these intermediate distributions between our model and p squared over q. P squared over q also has the density of our model, but we still target that. And then you draw samples with an yield importance sampling targeting this optimal importance sampling distribution, and you can show that your gradients have way lower variance. This shows, for example, the signal to noise ratio, and in red is the signal to noise ratio of our gradient estimator, and it has way more signal than even if you have exact samples from P. So this is importance sampling with exact samples from P, the target. If you want to estimate the alpha divergence with exact samples from the target, you get this thing, which is even worse than what we can do. So anyway, this works very well. I'm going to skip this in the interest of time, but we can see how it works. We have this target of is a mixture of Gaussians. You initialize it with a normalizing flow that starts sampling like this. If you minimize the Kullback-Leibniz divergence, you get this solution that misses modes. And if you use our method, you are able to cover all the different modes by minimizing this divergence. We also use a replay buffer to, once you generate samples with an yield importance sampling, you don't want to throw away those samples because it was expensive. And you can put them in a buffer and then sample from your buffer with probability proportional to importance sampling weights, and you can just reuse samples from your buffer. And every once in a while, you add new samples into your buffer. Okay? This works very well. We tried it to model this Alanine dipeptide. This is a common benchmark for simulating molecules. This is a small molecule, just an amino acid. And the key thing are these angles, phi and psi. This is a ground truth histogram of the distribution of those angles. The molecule is going to be vibrating and moving, and some configurations are more likely than others. And we see here some modes that are where the angles are quite likely to happen. You have very small modes here in this region, and this other region is empty. And if you train a flow on data, you will get this. And you can train a flow without data, with our method, and then doing importance sampling to eliminate bias, and we get perfect unbiased samples in this case, which is pretty amazing. This was actually the first time that people were able to obtain this level of accuracy for this molecule with a generative model. So yeah, we see that we have very high effective sample size, 92%, higher even than if you train the flow by maximum likelihood on exact samples from the target, which is pretty amazing. So just to conclude, some take-home messages. I have described this method. It's called flow and yield importance sampling bootstrap. It combines normalizing flows with an yield importance sampling, and it uses this replay buffer. It can sample from multimodal distributions. It trains from energies, not from data. It minimizes alpha divergences. And it only requires access to the target energy, not to samples. And it was the state of the art for fitting this molecule at this time. This is great, but there are many challenges, as I said. And obviously, one limitation of these models is that they are not scalable to high dimensions. In particular, an yield importance sampling is going to have high variance in high dimensions. So you need to be careful with that. The normalizing flows that I have described here are not very flexible. and they won't be able to work with very large molecules, and you will need more flexible models for that. I will talk about this later, tomorrow, and just as a brief thing, I want to mention that with some students and some collaborators, Gabor Chani, we started a company recently to implement generative AI to speed up the simulation of molecules. It's called Angstrom AI, and yeah, we're working actively in this area at the moment. So that's all. Thanks a lot, and if anyone has any questions, I'm happy to answer those questions.